The recording sign just went on, so I'll go ahead. This session is going to be fascinating. Zurich Instruments is playing two roles in this one, and it's doubly welcome, I think. We don't hear enough from basically test and measurement equipment companies who usually know more than most people about what's going on because they talk to all the labs and big industrial players. We ought to do that more often. But in this case, Zurich Instruments has actually been working in the quantum field for several years, which gives them something of a historical insight. And I think I know what quantum agnostic means, but rather than make a fool of myself and explain it, I'm going to let Stephan and Tobias speak. So we have Stephan Koch first. He's Vice President of Sales. And then Tobias Thiele. Is that how you pronounce it? And yes. And he's going to be speaking. Well, he's a quantum applications guy, so we're going to learn about where it can be used and how it can be sold to those applications. Both these gentlemen have advanced degrees. They went to something, and I'm afraid I don't know more about it than I should, called the Eidgen Österreichische Technische Hochschule Zurich, which I assume is a technical university in Zurich. But you both went there, and my little notes to myself said to mention that your group now is a spin-off from ETH, which is really the most distinguished industrial scientific lab in Switzerland. So thank you, and I'll hand it over to Stephan.
Yeah, thank you very much for the quick introduction. Thank you, Lawrence. Hello, everyone. Today, we would like to explore the question whether it is possible to shoot for qubit agnostic control electronics, whether it makes sense or it is desirable. We are Tobias Thiele and Stephan from Zurich Instruments, and we welcome you to our contribution to this marvelous virtual experience. We heard yesterday that measurement electronics outside of the Thiele fridge is becoming a problem. True, there are alternatives in the making and the future. However, the kind of problems that researchers are seeing today and they're speaking to us is not immediately about how many wires go inside the fridge. There are various approaches to scaling the number of qubits, and we, as an electronic maker, recognize that most of the research is still performed with common room temperature electronics. So, at VI, we design and manufacture quantum support quantum researchers around the world using our instruments. We try to implement it such as that the customers can focus on what they do best, which is doing science, not engineering of measurement electronics. The boxes look like this. This is a complex and well-balanced set of control electronics that support the control and the readout to one. On top of the hardware, there is a lot of software and signal processing that make the difference well. We'll come back to the topic of challenges and radio oscillations in the presentation. So, what is qubit agnostic electronics? As manufacturers, we call this the infrastructure that generates pulses and conditions the signals, so that are sent down to the qubit. It becomes agnostic of the physical implementation when you do not have to change large parts of the platform of the electronics when you go for a different platform. Ideally, you would like to cover all of them. However, we also see that the leaders in the quantum race, Google, IBM, all implement very specific dedicated control electronics. These are racks of electronics built for just a few applications in mind. Is this the way to go? We will try to answer this question. Is it possible to have such electronics? Is it desirable? Have they already come across that? It's where we would like to start with the first poll. We understand this audience is a very diverse crowd, and the insight we can get from that makes it even more valuable. Please select one or more statements of the poll that you think are correct or apply to you. I would not need Qubit Agnostic hardware since I concentrate only on one. I see advantages for Qubit Agnostic electronics, and I think the industry should aim at that. For me, agnostic electronics exists already. Qubit Agnostic hardware is not relevant and not an engineering problem. And you have also Joker, it is for your turf. Who cares? Scientists generally don't care because they are working on one platform and the likelihood of having a second or a third platform is so high. From the electronic makers, it's maybe nice because you can profit from certain economy of scale. From the benefit side, certainly profiting from the maturity that is implemented with one type of platform enables the other platform to have faster progress and maybe which ends up in the market. Does it already exist? Maybe not. Because if you look at 4 of the most common qubit implementations, and we categorize them according to the control, the way to control them, and the way to read out the qubits out, and maybe a few other requirements, we see that already atoms and circuit QED have a very different implementation. Reading out the electronics and the detectors are completely different. And the situation does not get better when you look at other platforms. We think that, have some hopes that circuit QED and spin qubits, we can maybe tackle them by one only set of electronics. But also this is very tricky because a synthesizer that spans over such a operation bandwidth with completely different amplitude or phase noise requirements is pretty difficult and challenging. You can aim for non-agnostic qubit control if you don't care about scaling. So if you have only one specific application to look at and not too many bits, or if you would like to if you don't address that, one of the top challenges in technology, because you are smearing your R&D efforts over several different battles. But at the end, it's about a question about efficiency. That you can focus better and you can implement better features if you go for a specific. However, applications want to be agnostic. So, for instance, Paolo Bianchi from Airbus, he would like to have access to a platform that implements a better performance, and he does not care about the effective qubit implementation. He wants to solve a mathematical, physical, or a financial problem. So our implementation of the qubit stack starts, of course, with the applications that are non-agnostic, and the qubit Qubit implementation in the bottom. And in between, there is our control electronics, the software associated in order to implement that. And the very important is the interfaces towards the towards the application. And certainly in between, we are heavily relying, or will be heavily relying on the interfacing standards, such as KISS or Q codes, to make sure that we are applying standards. What we do in the market, we listen to customers. No customer has told us he would like to use this quantum analyzer to read out transmons and optical photons at the same time. But what do they tell about the customers? They want to talk about time to experiment. So how long does it take for a researcher, for an implementer, between the moment he starts measuring and before he has the measure? For instance, a radio oscillation in half a day. We have proven how that works by using just the lower parts of the quantum stack, or for instance, something slightly more, but not too much, is a feedback in one day by doing some circles. And it can be then extended, as an example, using randomized benchmarking, where we have shown how a customer can implement this within 3 days by more of the quantum stack, and it gets a little bit more complex when you would like to do error correction, for instance, on a global level, when you need to personal coding and so on. And of course, you can then imagine to go towards quantum algorithms within a few months. It is certainly much better compared to what probably many people have been doing so far. They have used years in order to achieve that. What else is relevant for the customers? Scalability. So we have, out of published papers, customers implementing, for instance, first multiplex qubit readout back in 2015. And we've seen that, and working today on solutions and problems that implement about 20 qubit, we see an extrapolation of exponential growth, and looking at capabilities and implementations for 100 and 200 qubits. We call this the non-error corrected roadmap, and we also think that there is a second roadmap, which is error corrected. With a paper published in late 2019, with first implementation of logical qubit with a surface code detecting one error, and we also have commitments to scale this until 49 qubits error corrected within 2000. So this is where I'd like to hand over to my colleague Tobias, which is a little bit more technical than myself.
Okay, so thank you for this. Yeah, let's talk about another perspective where the scaling of quantum computers gets more and more complex, and this is the sequence, or the complexity of the sequences that you play on a single qubit. And if you look, for example, at the typical sequence, which was done about 10 years ago, this is well under control. It consists of maybe 2 pulses and a trigger line. So this is something which is easy to calibrate and also to control. But if you now look at the typical sequence nowadays, in the year 2020, this is a very different picture. So typical sequences today can have hundreds to thousands of pulses, where the amplitudes, phases, and frequencies need to be all individually tuned up. And this is just something that you cannot do on a single pulse level anymore. So where do we help out there, or what are the key challenges which we tackle there? So first of all, we ask ourselves, okay, what are the different customers? Okay, so there's this higher level customers or users of quantum computers which only want to solve, again, this mathematical problem, and they want to be completely qubit agnostic, as we learned before. And they just want to essentially define an algorithm which solves their problem, and they don't care whether it's it's actually implemented on a superconducting circuit quantum computer or an ion quantum computer. And then there's sort of this next level, which are much more in the topic of quantum computers and are managing the quantum computers themselves, and they want to define more the connectivity. So they really have certain boundary conditions given by their computer, and that's what they want to define. So they want to define whether qubit 1 is connected to qubit 2, and if a certain Hadamard gate from this higher level abstract algorithmic level is implemented by a certain sequence of gates, like a pi gate or a readout sequence. Okay, but clearly, again, no one really wants to calibrate all of these pulses or translate all of these pulses in a sample by sample basis, or even generate this big database which stores all these parameters. And this is exactly where we come in, and which is one of our visions, how we support users that use our quantum computing control system. And again, this starts up at this more agnostic level, where you just define this algorithm. That's where these different frameworks like Qiskit come to use. And then there's this much more detailed level where really the infrastructure and the architecture comes more into play. And this is something which really is expected to be different for many of the different quantum computers. Where we can really help all of them together is by translating this into this sample by sample sequence of pulses, and to generate this lookup table which stores frequency or amplitude of these pulses for all these different qubits. And all of this in the end has to be fully automated. So ideally, a customer or a user can just essentially define the connectivity of its quantum computer and then press a button, and then the system calibrates itself automatically. And this is sort of the vision, and that's where we are actively working towards. So this is one of them. So what is another big topic, and especially if you design your own control electronics, or you think or you want to buy into a company that makes them, or you want to just buy a quantum computing control system, one of the big questions is always feedback and error correction capabilities. So why do we want feedback and error correction? So currently, what the reason why people want to have feedback is for saving them valuable measurement time. So fast qubit reset is an application where after you control, or after your quantum algorithm, the qubit is in an undefined state, and you want to bring it back into a very well-defined state. And this you do by first measuring the state and then do a correction pulse. And this really saves you downtime of your quantum computer and helps you speed up your measurements. But something which is coming more and more important, and which is arguably probably the key thing which needs to be developed or shown for really scalable quantum computers is an error correction on a global level of your system. And this helps you to really improve the fidelity of your algorithm. You can define better logical qubits and so on. So feedback and error correction is really a key driver or a key decision argument. And what are the things to be careful about now? So one of the things to be careful now is that everyone that shows you, okay, we have the shortest feedback latency. And why is this the case? Well, the case it is, you can always, or almost always find a certain subset where you perform better than other people. But the problem is that the question about feedback is much more nuanced and can really depend in the end on the architecture and what you really want to implement and where you want to go with your system. So while it is good for marketing, one really has to think about what are the key aspects for feedback latency. And just to explain this or to demonstrate this a bit more at a hands-on experiment, hands-on example, and not just because it's a neat way of introducing our quantum computing control system. Let's have a look on the different feedback mechanisms that we think are important and how we implement them. So this is our quantum computing control system, a bit more spread out than in this nice box that Stephan showed in the beginning. And what you can see is we have 3 different types of instruments that are all, again, very specific, targeting a singular job, which they can do very well. The first one is our quantum analyzer, which can read out 10 qubits at the same time and in real time and with minimal latency. And then there is the arbitrary waveform generators, which you can use for control. And in the end, we have our central processing unit, which can couple all of them together. And you see again, the readout control and this central processing unit. This is again very well mapped in this table that Stephan showed in the beginning. So this is a recurring theme in how you plan your control system. So what are the different types of feedback you can do now? And now let's have a first look at this fast feedback. So this is this fast local feedback, which comes from which comes from that quantum analyzer essentially measures a set of qubit states and directly feeds them back to the control unit, which is the AWG. And then depending on in which states the qubits are, this control unit then decides whether it plays a pulse or not. So this is a very minimal, very short feedback path, but still there are several latencies that you need to figure out. And for example, travel time between the 2 instruments is typically negligible. And the real thing, which is really where you really pay the price, is in the way that you do your signal processing in the instruments. For example, how you read out, how fast you can process your readout data and distill these singular states. So this is one thing. And now this is a very local one. But now if you know really what is important for global error correction is this larger scale where the quantum analyzer measures a few sets of states and then they're distributed to this central unit. And then this central unit does a complicated, possibly complicated algorithm on it and generates then pulse sequences to correct at a very different location in the computer for this, for an error that happens. Okay. And this central unit is here really what is important to consider. And this can be simple lookup tables, but it can also be much more complicated processes like neural networks or minimal weight perfect matching algorithms. So different types of decoders which help you find out where the error occurred and how you correct this. And all of this has to be very fast, on the order of a few 100 nanoseconds. That's typically the benchmark that you want to get, and that's what we can provide with our solutions. Good. But in the end, what is the real thing that customers really want to do? They want to really push the limits always. And we are existing since a few years already now, but we are only recently new into the quantum field. But it is still the case, but now the customers are actually using heavily our instruments and producing more and more key results almost by the week by now. with our instruments. And the best way to just show how diverse these different applications are is just to pick out some of the very recent big results in the field and present them to you here now. So, for example, randomized benchmarking, I mentioned this is one of these most demanding in terms of memory sequences for your control system. And this is now a standard technique that can be done with our instruments. And then recently people have worked on solving NP-complete problems with this quantum approximate optimization algorithms. So they try to tackle really hard problems now using our control software. In addition, there is people working on the more technical level to really try to make pulses as short as possible. This is important because the shorter you can make your pulse while still maintaining a high fidelity, you can fit more and more pulses sort of within your coherence time, so you can tackle more and more complicated problems. This is a very nice result from IBM recently, also that used our system. And then in the end, there's the cryoscope. So in every system, in every cryostat, you typically address certain distortions of your pulses, and they limit the fidelity of your 2-qubit gates. For example, for flux pulses, that's a very typical problem, or typical problem that people fight off. And very recently, people have indeed found out how to best characterize these distorted pulses at the cold chip, and use our real-time precompensation. And this is really an example of this targeted focus that we really solve this problem. So with our real-time precompensation, they could really improve on the fidelity of their 2-qubit gates. And this you can see here. And the only thing which you need to really realize is that this is here you have much more yellow than on the left side, which means you have a much higher fidelity in your 2-qubit gates. Good. So with this, I would like to finish, but before finishing, let's now put our answer to whether qubit agnostic control electronics exists, and to put it in a challenging way. Now we think it's a waste of money, and it's very interesting that this, I think, was not reflected in the poll. So something we really thrive off, and which we really use to advance ourselves, is to challenge others, but also be challenged. So we hope that you can challenge us now in the following question and answer session. So with this, I would thank you all for listening in and tuning in.
Thank you so much. Lawrence, you can come back on camera.
Yeah, here I am. So not quite sure from clock on this thing quite how long we've got, but there are plenty of questions. So, there are even more since I looked down. One question from one of our attendees is, so are you guys already actually working with customers, which is the first part of the question. The second part is, can you tell me who they are? And it's okay if you say no comment. So I think that question's, well, I guess it's really for Stephan. Yeah. Mm.
Yeah, with pleasure. I saw as well from who the question came. Thank you, Paolo, for asking that. No, certainly. There are plenty of published papers, and probably have been in quantum technology a bit longer than Tobias said. I think we've been in quantum technology for the last 10 years, or it may have been called nanotechnologies.
Okay.
It's only recently it moved towards low qubit research and so on. Now, certainly the papers that you have seen that Tobias has disclosed are either from IBM, from Delft, or from the other one, and Chalmers. So yes, plenty of customers, and they start somewhere in Taiwan and end somewhere in California. So that's a short answer to you.
Well, okay, let me ask another question. This one's from John Levy. It's Seek, and you would have almost certainly guessed that one too. I'll read what John said. Can ZI work with, well, the question's changed. Basically with their technology, their non-CMOS technology, SFQ, which is naturally quantized picosecond pulses instead of microwave pulses. Can they measure at speeds about 40 gigahertz?
Yeah.
I would say that's a Tobias question.
Yeah, exactly. So, I have to be honest, we haven't evaluated whether we can work with the superconducting or SFQ technology. So currently the way that this works is more on this conventional way that we generate in the end analog waveforms, but it is true that essentially everything we do is on the digital level. So per se, one probably would have to think about the interface and how we convert this digital our digital knowledge into these short picosecond pulses. But in principle, we work with, I don't see that these two technologies are completely incompatible. And in general, for whether we measure at speeds of higher than 40 gigahertz, given sort of these boundaries, let's say we are, so most of our instruments are in baseband, so typically work on less than gigahertz, but we of course listen very carefully into what customers want. Again, that's one of our leads, and this is and sort of higher frequency components or going into higher frequency is definitely something which we can at least keep an eye on. Let's say it like this. But it will be up to 40 gigahertz. I think it's in the end a question of how we transfer our digital domain to this frequency regime.
Response back from Paolo. Thank you. Great. I assume this means the ZI solution is affordable and hence is having success. So I don't know if either or both of you, again, I assume that's a Stephan question, if it's a question.
Frankly speaking, I'm always very impressed by seeing how many people are now moving into qubit research or qubit-like research, and they use various types of mechanisms and approaches in order to read them out. There's not only one way. And this actually permits us to have a large impact on various type of customers. And we tend to see that various instruments apply for different applications, which clearly we like to have this provocative statement. There is no qubit agnostic electronics because of the various applications and the various type of qubit platforms. Nevertheless, it's good to support them all, but the electronics per se is pretty much different. It does a different DSP.
Well, another question which has came up in your talk towards the end. We did that poll, and the people who thought that qubit agnostic electronics, control electronics, was very important, was fairly low compared with the people who thought it wasn't important. What's your reaction to that? Actually, both of you. I mean, is it, oh gosh, we've gone down the wrong road, or this really is kind of, you know, has to be a targeted technology? And I suppose the third part of that is, you know, what's the target? You sort of said that, but maybe you could elaborate a little bit more.
I go for 30 seconds and then you 30 seconds, Tobias.
That's fine.
I understand that probably the attendees to this event would like to have a qubit agnostic electronics or qubit agnostic quantum stack, and this is absolutely fine. This is absolutely what we need to shoot at. And then when it comes to the pure electronics, we see that the current way of manipulating the individual qubits is so much diverse for the different platforms that we are a good step away from that. Tobias, what's your take on it?
Yeah, I think it would be interesting to do the poll now after our talk. But
I don't know if we can do that or not, but yeah,
it's but maybe better not. No, so I think our point is really we are definitely shooting for the agnostic higher level stack, but. And I think this is really a key thing. So I think you really have to this quantum race, if you tell it, it's very fast advancing, and you really have to think well where you put your resources. And I think you better put your resources there where you can really solve the hard problems than try to artificially or realistically diversify yourself over very few platforms. And this is essentially the key message here. So if you're someone who wants to, I don't know, who invests into a company who promotes qubit controller electronics, at least if I would do this, I would ask myself, is this really a sustainable pathway, or are my resources really well spent to really solve the hard problems? And so this is sort of my take on this. So I think on this control level, you really have to tackle the hard problems, and you have to do this in a very focused way, and not trying to solve all the different problems for all different platforms which they exist.
The poll seems to be going in a different direction this time, which is interesting. So you're obviously persuasive talkers. So I to say my clock doesn't seem to be telling me what I need to know, but
you still have 5 minutes.
It seems to be at least. Yeah, and this is saying something else. I don't know what's going on, but right, that's what I figured, about 5 minutes. You know, I've been around test and measurement companies for a while. Can you still hear me?
Yes, yeah.
Okay, I don't know what happened there. And my perception of how they operate from a business strategy point of view is they're all out there searching for the next standard to test, because I was in telecom and it's all about standards, and then I've seen it in other things too, in material science. Is quantum the next big thing to chase for test and measurement companies? You've obviously been doing it for quite a while, 6, and you said possibly longer, but is this the next big thing in your niche of the electronics industry?
Definitely, but not for the entire market. Quantum technologies, or making quantum implementation, is growing, certainly, and you see as well a certain number of competitors and companies doing that, and this will further grow. But let me say that it will never reach the size of 5G or communication standards and needs, because for the moment it's much less impact. Then I can talk about what happens in 5 years. I wouldn't know. Nevertheless, it's certainly a very challenging time right now to follow the customer expectations and this kind of linear growth in the logarithmic scale usually are very difficult to keep up with, right? Need to be tackled with a very dedicated focus. Finally, you can succeed, and you try to select your battles when it comes to what kind of implementation is needed. But certainly, summarizing, it's a very...
Stephan? I'm so sorry to interrupt. Would you be able to hold your microphone steady while you are talking? That might help with your audio.
Yeah, already Ben has I'm sorry for that.
No, it's good.
The microphone wasn't for the standard of this presentation. Sorry for that.
No, but essentially to add to this, I think it's we're always looking for challenges. I think this is true. So I think this campaign of challenge us is not comes from somewhere. We always try to be one of our guidelines, sort of be the reference, and I think quantum is definitely a very challenging field, and with a lot of potential, of course, a lot of risk. But this is something which really, I think, motivates us all.
Maybe this is a carry-on question, but I'm impressed by how early you guys got into it. What got you into the quantum field? And you'd said it came out of your nano group, and a lot of us, I think, went from nano to quantum. But is that the history, or was there more strategic thought or engineering thought around that?
Tobias?
Shall I? Okay, I haven't, so a disclaimer first, I haven't been around that long in the company, so Stephan will have to correct me. No, but essentially how we got into this superconducting quantum business a few years ago, it's really from that we realized that something where we are very well performed and sort of are the standard or the reference in the field is login techniques, and for reading out these superconducting circuits, and this is typically a login technique. So what you do is you up convert and then do a down conversion to a IF frequency of a few hundred megahertz, and then you digitize this, and then there's some signal processing. And we knew already very well and had essentially a platform how to do this. And so in this case, this was sort of our entry point into this quantum race, where because we just realized, okay, we can really make a difference there with the know-how that we had. That's sort of my point of in this.
We're running out of time fast, but I think we've got time for one more question. Obviously quantum agnostic is very important to you. I assume that a quantum agnostic machine is more expensive than a quantum specific machine, if that's the opposite. Qubit, I'm sorry, not quantum. Although it's the same thing. Are these big differences, or what?
Trying to. We think that it will be very hard and very from the implementation point of view, engineering point of view, very difficult to do 4 platforms, ions, color centers, spins, and circuit QED with exactly the same hardware, especially because different timings, different power requirements, different analog performance requirements, different frequencies, different software, and so on. Eventually this will come, probably, but it is not what our customers are particularly interested in at the moment. So we are not shooting necessarily. Anyway, thank you for the questions, and as all other participants to the conference have said, we are reachable by the Slack channel and any other media.
Perfect. Thanks a lot also from my side.